Good morning, everyone. I am Dr.R.Hemamalini, Associate Professor, Department of Physics, Sri Sarada College for Women, Autonomous, Salem 16. Now I am going to deal with the topic oscillators. Introduction to feedback. The phenomena of feeding a portion of the output signal back to the input circuit is known as feedback. The effect results in a dependence between the output and the input, and an effective control can be obtained in the working of the circuit. Feedback is of two types: negative feedback and positive feedback. Negative or degenerate feedback. In negative feedback, the feedback energy is out of phase with the input signal and thus opposite to it. Negative feedback reduces gain of the amplifier. It also reduces distortion, noise, and instability. This feedback increases bandwidth and improves input and output impedances. Due to these advantages, the negative feedback is frequently used in oscillators. Negative feedback circuit is shown here in this slide. In the figure, the gain of the amplifier is represented as A. The gain of the amplifier is the ratio of the output voltage V0 to the input voltage Vi. The feedback network extracts a voltage Vf is equal to beta V0 from the output V0 of the amplifier. This voltage is subtracted for negative feedback from the signal voltage Vs. Now Vi is equal to Vs plus Vf, that is equal to Vs plus beta V0. The quantity beta is equal to Vs by V0 is called as feedback ratio or feedback fraction in oscillators. Positive feedback circuit is shown here. Positive or regenerative feedback. In positive feedback, the feedback energy is in phase with the input signal and thus aids it. Positive feedback increases gain of the amplifier, also increases distortion, noise, and instability. Because of these disadvantages, positive feedback is seldom employed in amplifiers, but the positive feedback is used in fraction in oscillators. The output V0 must be equal to the input voltage Vs plus beta V0 multiplied by the gain A of the amplifier. Hence, Vs plus beta V0 into A is equal to V0. AVs plus A beta V0 is equal to V0. AVs is equal to V0 into 1 minus A beta. V0 by Vs is equal to A by 1 minus A beta. Barkhausen criterion. The condition A beta is equal to 1 is known as Barkhausen criteria. It implies the magnitude of the loop gain AB is equal to 1 and phase shift over the loop is equal to 0 or 360 degrees. Frequency of the noise in the amplifier for which this criteria are satisfied is the frequency of oscillations. Basic RC phase shift oscillator circuit is shown here. The RC phase shift network is in the dotted line. The RC oscillator, which is also called as phase shift oscillator, produces a sine wave output signal using regenerative feedback from the resistor capacitor combination. This regenerative feedback from the RC network is due to the ability of the capacitor to store an electric charge, similar to the LC tank circuit. This resistor capacitor feedback network can be connected as shown above to produce a leading phase shift or interchanged to produce a lagging phase shift. The outcome is still the same as the sine wave oscillations, only occur at the frequency at which the overall phase shift is 360 degree. By varying one or more of the resistors or capacitors in the phase shift network, the frequency can be varied, and generally this is done using a 3-ganged variable capacitors. If all the resistors R and the capacitors C in the phase shift network are equal in value, then the frequency of oscillation produced by RC oscillation is given by F is equal to 1 by 2 pi R root of 2n, where F is the output frequency in Hertz, R is the resistance in ohms, C is the capacitance in farads, N is the number of RC stages. Here N is equal to 3 conditions perfectly square waveforms. Since the resistor capacitor combination in the RC oscillator circuit also acts as an attenuator, producing an attenuation of minus 1 by 29th V0 by Vi is equal to beta per stage, the gain of the amplifier must be sufficient to overcome the losses, and in our 3 mesh network above, the amplifier gain must be greater than 29. The loading effect of the amplifier on the feedback network has an effect on the frequency of oscillations and can cause the oscillator frequency to be up to 25% higher than the calculated. Then the feedback network should be driven from a high impedance output source and fed into low impedance load such as common emitter transistor amplifier, but better still is to use an operational amplifier as it satisfies these conditions perfectly. Types of oscillators. There are many types of oscillators but can broadly be classified into two main categories: harmonic oscillators and relaxation oscillators. In harmonic oscillators, the energy flow is always from active component to the passive component, and the frequency of oscillation is decided by the feedback path, whereas in a relaxation oscillator the energy is exchanged between the active and the passive component, and the frequency of oscillation is determined by the charging and discharging time constant involved in the process. Further, harmonic oscillators produces low distorted sine wave output, while the relaxation oscillator generate non-sinusoidal, sawtooth, triangular or square waveforms. The main type of oscillator include RC oscillator, Wien bridge oscillator, RC phase shift oscillator, LC oscillator, Hartley oscillator, Colpitt's oscillator, Clap oscillator, crystal oscillators, etc. Wien-bridge oscillator. A Wien-bridge oscillator is a type of phase shift oscillator which is based upon a Wien-bridge network comprising of four arms connected in a bridge fashion. Here, two arms are purely resistive while the other two arms are combination of resistors and capacitor in phase. One arm has resistor and capacitor connected in series R1 and C1, while the other arm has them in parallel R2 and C2. This indicates that these two arms of the network behave identical to that of high pass filter or low pass filter, mimicking the behavior of the circuit shown by figure. In this circuit, at high frequencies, the reactance of the capacitor C1 and C2 will be much less due to which the voltage V0 will become 0 and R2 will be shorted. Next, at low frequencies, the reactance of the capacitor C1 and C2 will become very high. However, even in this case, the output voltage V0 remains at 0 only. As the capacitor C1 would be acting as an open circuit, this kind of behavior exhibited by the Wien bridge network makes it a lead lag circuit in the case of low and high frequency respectively. Wien bridge oscillator frequency calculation, that is, nevertheless amidst these two high and low frequencies there exists a particular frequency at which the values of the resistance and the capacitive reactance will become equal to each other, producing the maximum output voltage. This frequency is referred to as resonant frequency. The resonant frequency for a Wien bridge oscillator is calculated using the following formula: Fr is equal to 1 by 2 pi root of R1 C1 R2 C2. If R1 is equal to R2 is equal to R and C1 is equal to C2 is equal to C, then Fr is equal to 1 by 2 pi RC. Further, at this frequency, the phase shift between the input and the output will become 0 and the magnitude of the output voltage will become equal to one-third of the input value. In addition, it is seen that the Wien bridge will be balanced only at this particular frequency. In the case of Wien bridge oscillator, the Wien bridge network is shown in the figure will be used in the feedback path as shown in figure. The circuit diagram for a Wien bridge oscillator using a BJT shown below. In this oscillator, the amplifier section will comprise of two stages, that is formed by the transistor Q1 and Q2, wherein the output of Q2 is backfed as an input to Q1 via Wien bridge network. Here, the noise inherent in the circuit will cause a change in the base current of Q1, which will appear at this collector point after being amplified with the phase shift of 180 degree. This is fed as an input Q2 via the C4 and gets further amplified and appear with an additional phase shift of 180 degree. This makes the net phase difference of the signal fed back to the Wien bridge network to be 360 degrees, satisfying the phase shift criterion to obtain the sinusoidal oscillations. However, this condition will be satisfied only in the case of resonant frequency, due to which the mean bridge oscillator will be highly selective in terms of frequency, leading frequency stabilized. Wein bridge oscillators can even be designed using op-amp as a part of their amplifier section as shown in the figure. However, it is to be noted that here an op-amp is required to act as a non-inverting amplifier, as the Wein bridge network offers zero phase shift. Further from the circuit, it is evident that the output voltage is fed back to both inverting and non-inverting input terminal. At resonant frequency, the voltage applied to the inverting and non-inverting terminals will be equal and in phase with each other. However, even here the voltage gain of the amplifier needs to be greater than 3 to start oscillations and equal to 3 to sustain them. In general, these kind of op-amp based Wein bridge oscillator cannot operate above 1 MHz due to the limitation imposed on them by their open loop gain. The Wein bridge oscillator using an op-amp shown here. Wein bridge networks are low frequency oscillator which are used to generate audio and sub-audio frequencies ranging from 20 Hz to 20 kHz. Further, they provide stabilized low distorted sinusoidal output over a wide range of frequency, which can be selected using decade resistant boxes. In addition, the oscillation frequency in this kind of circuit can be varied quite easily, as it just needs variation of the capacitor C1 and C2. However, these oscillators require large number of circuit component. RC phase shift oscillator use resistor capacitor RC network to provide the phase shift required by the feedback signal. They have excellent frequency stability and can yield a pure sine wave for a wide range of loads. Ideally, a simple RC network is expected to have an output which leads to the input 90 degree. However, in reality, the phase difference will be less than that, as the capacitor used in the circuit cannot be ideal. Mathematically, the phase angle of the RC network is expressed as phi is equal to tan inverse of XC by R, where XC is equal to 1 by 2 pi FC is the reactance of the capacitor C and R is the resistor. In oscillator, these kind of RC phase shift network, each offering a definite phase shift, can be cascaded so as to satisfy the phase shift condition led by the Barghasan criterion. Here, the oscillator resistor RC limits the collector current of the transistor resistor R1 and R nearest to the transistor from the voltage divider network, while the emitter resistor Re improve the stability. Next, the capacitor Ce and C naught are emitter bypass capacitor and the output DC decoupling capacitor respectively. Further, the capacitor also show 3 RC network employed in the feedback path. This arrangement causes the output waveform to shift by 180 degree during its course of travel from output terminal to the base of the transistor. Next, this signal will be shifted again by 180 degree by the transistor in the circuit due to the fact that the phase difference between the input and output will be 180 degree in the case of common emitter configuration. This makes the net phase difference of 360 degrees, satisfying the phase difference conditions. One more way of satisfying the phase difference condition is to use for RC network, each offering a phase shift of 45 degree. Hence, it can be concluded that the RC phase shift oscillator can be designed in many ways, as number of RC network in them is not fixed. However, it is to be noted that although an increase in the number of stages increases the frequency stability of the circuit, it also adversely affects the output frequency of the oscillator due to the loading effect. The generalized expression for the frequency of oscillation produced by RC phase shift oscillator is given by F is equal to 1 by 2 pi RC root 2n, where n is the number of RC stages formed by the resistor R and the capacitor C. Further, as in the case of for most of the oscillator, even RC phase shift oscillator can be designed using an op-amp as it's part of the amplifier section as shown in the figure 3. Nevertheless, the mode of working remain the same, while it is to be noted that here the required phase shift of 360 degree is offered collectively by the RC phase shift network and the op-amp working in the inverter configuration. Further, it is to be noted that the frequency of the RC phase shift oscillator can be varied by changing either the resistor or the capacitor. However, in general, the resistors are kept constant while the capacitors are gang tuned. Next, by comparing the RC phase shift oscillator with the LC oscillator, one can note that the former uses more number of circuit components than the latter one. Thus, the output frequency produced from the RC oscillator can deviate much from the calculated value rather than in the case of LC oscillator. Nevertheless, they are used as local oscillator for synchronous receiver, musical instrument, and as a low and or audio frequency generator. Hartley oscillator is a type of harmonic oscillator which was invented by Raphael Hartley in 1915. These are the tuned circuit oscillator which are used to produce the waves in the range of radio frequency and hence are also referred to as RF oscillators. Its frequency of oscillation is decided by its tank circuit, which has capacitor connected in parallel with the two serially connected inductor as shown in the figure. Here, the RC is the collector resistor, while the emitter resistor RE forms the stabilizing network. Further, the resistor R1 and R2 form the voltage divider bias network for the transistor in common emitter CE configuration. Next, the capacitor Ci and C0 are the input and output decoupling capacitor, while the emitter capacitor Ce is the bypass capacitor to bypass the amplified AC signal. All these components are identical to those present in the case of common emitter amplifier, which is biased using a voltage divider network. However, figure also shows one more set of component wise, the inductor L1 and L2 and the capacitor C, which the tank circuit shown in red enclosure. On switching on the power supply, the transistor starts to conduct, leading to an increase in the collector current IC, which charges the capacitor C. On acquiring the maximum charge feasible, C starts to discharge via inductor L1 and L2. This charging and discharging cycle results in the damped oscillation in the circuit. The oscillation current in the circuit produces an AC voltage across the inductor L1 and L2, which are out of phase by 180 degree as their point of contact is grounded. Further, from the figure, it is evident that the output of the amplifier is applied across the inductor L1, while the feedback voltage drawn across L2 is applied to the base of the transistor. Thus, one can conclude that the output of the amplifier is in phase with the tank circuit's voltage and supplies back the energy lost by it, while the energy fed back to amplifier circuit will be out of phase by 180 degree. The feedback voltage, which is already 180 out of phase with the transistor, is provided by an additional 180 degree phase shift due to the transistor action. Hence, the signal will appear at the transistor output will be amplified and will have a net phase of 360 degree, 180 plus 180, 360 degrees. At this state, if one makes the gain of the circuit to be slightly greater than the feedback ratio given by beta is equal to L1 by L2, if the coils are wound on different cores, beta is equal to L1 plus M by L2 plus M. If the coils are wound on the same core with M indicating the mutual inductance, then the circuit generates the oscillation which can be sustained by maintaining the gain of the circuit by equal to that of the feedback ratio. This causes the circuit in figure to act as an oscillator as it would then satisfy both the condition of Bargason criteria. The frequency of such an oscillator is given by F is equal to 1 by 2 pi root of LEFFC. LEFF is the effective series inductance, which is expressed as LEFF, that is equal to L1 plus L2. If the coils are wound in on different cores, LEFF is equal to L1 plus L2 plus 2M if the coils are wound on the same as core. Hartley oscillators are available in many different configurations, including series or series fed, common emitter or common base configured, and BJT or FET amplifier based. Further, it is to be noted that the transistor based amplifier section shown in figure can be replaced by an amplifier of another kind, like that of inverting amplifier formed by op-amp as shown in figure. The working of this kind of oscillator is similar to that of the one shown earlier. However, here the gain of the oscillator can be individually adjusted using the feedback resistor RF, due to the fact that the gain of the inverting amplifier is given as minus RF by R1. From this, it can be noted that in the case the gain of the circuit is less dependent on the circuit element of the tank circuit. This increases the stability of oscillation at the oscillator in terms of its frequency. Hartley oscillator using an op-amp is shown in figure. Hartley oscillators are advantageous as they are easy to tunable circuit which are very few components, including a capacitor and either two inductor or a tapped coil. This results in a constant amplitude output throughout its wide operational frequency range, which typically ranges from 20 kHz to 30 MHz. However, this kind of oscillator is not suitable for low frequency, as it would result in a large sized inductor which makes the circuit bulky. Further, the output of Hartley oscillator has high content of harmonics in it and hence does not suit for application which require pure sine wave.
Now I am going to deal with oscillators. An oscillator is a circuit that produces a repetitive signal from a DC voltage. The Colpin's oscillator is known for using a capacitor voltage divider as its feedback source. Now, Colpin's oscillator R1, R3 plus VCC, R2, R4, C4, C1, C2 and inductor or connector like this. This is the amplifier circuit with feedback connector. The Colpin's oscillator is a type of oscillator that uses an LC circuit in feedback loop. The feedback network is made up of a pair of tapped capacitors C1 and C2 and produces a feedback necessary for oscillations. The output voltage is developed across C1. The feedback voltage is developed across C2. The frequency of oscillation Fr is equal to 1 by 2 by root LC, that is LCT, that is CT is equal to C1 C2 by C1 plus C2, that is total capacitance. Conditions for oscillation and startup, values of C1 and C2 determine the attenuation as V is equal to Vf by V0, that is very much equal to Ixc1 by Ixc2, that is Xc1 by Xc2, that is equal to 1 by 2 by Fr C1 by 1 by 2 by Fr C2, or V is equal to C2 by C1. But for oscillations, AB beta is equal to 1, that is equal to AB is equal to C1 by C2. For the oscillations to be self-starting, AB beta is equal to greater than 1. Input impedance of the amplifier acts as a load on the resonant feedback circuit and reduces the quality factor of the circuit. Fr is equal to 1 by 2 by root of LCT root of Q square plus 1. Fr is equal to 1 by 2 by root LCT. Thank you.
Teach you that NAND
NAND as NOR gate, universal building block. To build op-amp and exclusive OR XOR gate using if NAND and NOR gates, to build OR, NOR and XOR with NAND, and here we are using this kit. Okay, this is a circuit diagram, and here first you have to pin in all these ICs, that is 7400, and you have to connect likewise. Okay, then in A input you are connecting both 1 and 2, and you are getting y is equal to A dot A bar dot A bar is equal to A bar. So the truth table is given here, and NAND as AND gate. The NAND as AND gate, that is 2 AND gates. You have this NAND gate and this NAND gate, and here it is tied together. You have the truth table A, B and Y. A is equal to 0, B is equal to 0 and Y is equal to 0. And 0, 1 will give you 0, and 1 and 0 will give you 0. 1 and 1 will give you 1. And NAND as OR gate. In the NAND as OR gate, you have 2 NAND gates connected with the another NAND gate. So totally you have 3 NAND gates, and the truth table for that is given here as A, B, Y, that is 0, 0 and 0. And 0, 1 will give you 1, and 1 and 0 will give you 1, and 1 and 1 will give you 1. And the other one is NAND as XOR. So the circuit diagram for NAND as XOR is given here, and the connection is so made, and it is shown here. And the truth table A, B and Y 0, 0, 0, 0, 1, 1, 1, 0, 1 and 1, 1, 1. Thank you.
0 0 0 0 0 0 0 0 0 0 0 1 1 0 1 1 1 0 1 1 0 1 1 1 1 1 1 1 1
Thank you, one and all.